The Steiner tree problem is very similar to the minimal spanning tree problem. Imagine that you have a weighted graph G with vertices V and edges E, and a subset of vertices V prime in that graph. A Steiner tree is any connected tree that contains all the vertices in V prime. The difference between the Steiner tree problem and the minimal spanning tree problem is that the Steiner tree can include any vertex in V. These extra intermediate vertices are known as Steiner points, or Steiner vertices. The subgraphs below are Steiner trees. They use all of the selected vertices as well as some extra ones.
Why is a Steiner tree a combinatorial optimization problem? To satisfy the conditions of a combinatorial optimization problem, a problem must have a set of states, a cost function, and a goal. The set of states comprises all the Steiner trees that exist within the graph. The cost component comprises the weight of each Steiner tree, and the goal is to minimize this weight. Through these three properties, we have a combinatorial optimization problem.
So the decision version of the Steiner tree problem asks, is there a Steiner tree such that the weight of the tree is less than some value W? Now, for the purposes of illustration, let's just say W is 20. So now we have to try and find a Steiner tree such that the weight is less than 20. So for this example, if we use these three nodes and connect them like so, we end up with a tree whose weight is 14. Now, the optimization version of the Steiner tree problem asks for the best tree. In this case, that means that out of all the possible Steiner trees, what is the one with the least weight? Now, out of all of these Steiner trees, it looks like the first one is the best.
Our Steiner tree algorithm uses a process called simulated annealing. If you look at the pseudocode, I'm going to explain it later with an example, but first, we run our algorithm keeping track of the annealing probability. If a cycle exists in the graph equals false, and if the required nodes are connected equals true, we save that specific Steiner tree with a unique ID and weight. Then we remove a random edge, place it in the removed edge stack, and if the required nodes are connected equals false, which in this case would mean that we've broken off one of the required nodes from the Steiner tree, we put the removed edge back, and then we put back a percentage of edges from the stack of previously removed edges based off of the current probability, and then we decrease the probability. Here's an example. First, I draw out a random Steiner tree with 6 different points and with weights amongst those nodes. The green nodes are the required nodes in the Steiner tree. I'm labeling the nodes just to make it easier to follow the progression. Next, I create a stack for which the disregarded edges are going to be placed in. I randomly remove edges following my algorithm. We still have cycles, so I'm removing the edges, and now we get to our first possible Steiner tree. Steiner tree ends up having a weight of 33. And we get to it because of the fact that we have no cycles and all of our required nodes are connected. The simulated annealing probability we start off with is 0.5. This value can be adjusted for different results, but will decrease as we pop edges off the edge stack and put them back into the graph, as I'm doing right now. Then I will decrease the simulated annealing probability. This is all based around the statistical probability and idea that as we progress in the algorithm, we won't want to place as many edges back because we will getting to subsequently lower and lower local minimums. This is not a perfectly random example because I'm arbitrarily picking values to remove, but in an algorithm, we would randomly pick edges to take off and place on the stack. Now that I'm popping edges back off, I'm going to decrease the simulated annealing probability again, and then we'll randomly start removing edges from the graph. Removing edges 1, 3 and edge 4, 6, which then results in another tree, which is another possible Steiner tree with a weight of 26. As you can see, even though this is not a perfect example, our process is slowly decreasing the weight. We're going to continue to move forward in this way I write out ... 0.001 to showcase that we're going to continuously be taking edges off the graph, putting them on the edge stack, finding that there's a disconnect from one of the required nodes, and then having to put it back on to the graph, which is going to decrease the simulated annealing probability even more. Eventually, though, we will finally get to a point where we have such a low simulated annealing probability that we will not be able to decrease the possible Steiner tree's weight anymore, which is what I'm showing with this decreasing exponential function. Our best result then is a weight of equals 18.